Welcome to homework.
In this problem, we have a beam that is pinned at the left end. It has a ball roller support in the midspan, 15 feet from this end. We have an applied load acting at an angle on the right end, and then a distributed linearly varying load acting over the first 15 feet over here. And this is kind of the problem's kind of a pain because we're asked to take a look at it, make a cut through this distributed load. So we're going to have to look at the resultant forces and moments twice. And so then we want to look here and here. So what we can do is I can use just vectors to make things write things a little more simply. And we have, I'm going to use this as my origin. And then R2 out here is 25 feet to the right. R3, so what I'm going to do with this distributed load is divide it into a uniform load and a linearly varying part. So the uniform load has a resultant force acting at the center of the uniform load, and the triangular linearly varying load has a resultant force acting 1/3 of the way in from this side, so that would actually be 5 feet, which is what we have here. So that actually, the resultant moment of the linearly varying part is produced when this load is 5 feet from the end. And then this load is at 7.5 feet from the end. And then F5, where the roller is 15 feet. So then we have our forces, and we have two components of force in the at the pin. The applied load is at a 5, 12, 13 angle, so we know it has a magnitude F2, and here's the unit vector that describes the direction. F3 is the triangular portion here on top. So this distance here, this value here is 60 minus 40 pounds per foot. So we get 20 pounds per foot times 15 feet divided by 2 because it's a triangle. So that's our area under that enclosed by the triangular region. Now the rectangular region, this has a height of 40 pounds per foot, and it acts over a region of 15 feet. And then F5 is our reaction at the roller. Now, we also have where I have, if we're going to look at this cut here, so I took a cut here, and for whatever reason, I looked at this side. I took a free body diagram of that side, and it would probably have been simpler to use the other side, but again, it doesn't. It's just a matter of whether how much simpler the algebra is. Your answer shouldn't be any different, and it's a good way to check. So the position of this is 20 feet from the end, and then because I have let's see here. I actually did it. I switched things, so these should all be plus. So because these are all positive, because we have a positive normal here. So we have a positive shear, a positive normal force, and a positive moment. Now we have all of these forces, and well, we also have. We'll deal with these guys in a minute, or these ones. And so we can sum forces and moments on the whole thing, and then on just a piece of it. So doing the whole thing, we get that F1 is 265 pounds in the horizontal direction and minus 24.6 pounds in the vertical direction. And the roller has a force in the vertical direction as 1,410 pounds. So those are our constraint forces here. And now what we can do is look at the at the loads acting on this section here. And we can see that we have F1, F3, F4, and F5 acting over here. So what I did is I just said, okay, we're going to sum over all the previous forces as of 1, 3, 4, and 5. And then we also have now P1 acting. So that is our internal force. And then likewise we have moments. And so I'm going to sum all the moments over from force 1, 3, 4, and 5. Sum the moment, add that the moment caused by our internal load where we took the cut, and then add the point moment acting at this point, and then set that to 0. So this gives us another 3 equations, and we can figure out the 2 components of P1, and then we can also figure out M1. And P1 is 265 pounds, minus 265 pounds in the vertical direction, and minus 637 pounds. Sorry, this is in the horizontal direction, this is in the vertical direction. The moment is minus 3,180 pound-feet. And then we can take a look at this part here, which we have to kind of redo some stuff. And in this case, we have this, and we have a different region of this distributed load because it only goes over 12 feet. So what we have then is we need to consider what I've called F3 prime and F4 prime. Okay, so those are different than these. This one now is acting at a distance of 4 feet in, and this one is acting at a distance of 6 feet in. I'm not sure why I have this so skewed, but anyway, this would be 6 feet and this would be 4 feet. I don't know. I didn't actually write those down, but we can then sum forces over this section here. So what we're going to have is, this would be, let's see, what was that value? I think this was 52. I have to look. Let me see here what that value was. I didn't write it down. Let me see here. Yeah, well, basically what I just, just looking at my notes, this curve here is defined by 60 minus, let's see here, that would be 4/3 x. So 60 minus 4/3 x. So if x is 12, then 4/3 of that is 16. So 60 minus 16 is 44. This is 44. So we have the load given by the rectangular region, and then the difference here between 60, this would be 60 minus 44. So, and again, we know where they're acting, and so we can just sum forces and moments. And again, I said we're summing forces from over loads 1, 3 prime, and 4 prime, and moments over 1, 3 prime, and 4 prime. Then we have our internal reactions, and we get 3 more equations for 3 more unknowns, and P2 is minus 265 pounds in the horizontal direction and 649 pounds in the vertical direction, and the moment at that point, the bending moment, is minus 4,230 foot-pounds.